So the first thing here, I'm just going to show you an animation of the shells. The one for the washers, discs, and cross sections we did last year. You can find those in the Schoology folder for Unit 1, and it says animations. But because shells are new, good thing about shells is the AP test doesn't test them, and I won't test them, but I still like to expose you to everything. If you were in a college course, you would have had disc, washers, then shells. So, I just at least want to expose you to it. So we use shells when it's easier to find your volume by going, instead of perpendicular to the axis of rotation, so we're going to picture this one up here, rotating about the y-axis. We draw a representative rectangle perpendicular. And then what we do is we still consider one of those rectangles. So you'll see that one of these I think is going to shade in green. And you picture whipping that around the y-axis. Now if I did that for each one of those rectangular pieces, I would get the volume of the revolved solid. I was telling them it's like cutting into a cake from the outside and doing like it's hard to show you when you can't see my fingers. It'd be a dumb way to cut a cake, I said, but you could do it by giving you a slice by cutting in and just going around the inside of the cake. If you were to cut the cake from the bottom up, everyone would get a circle. If you were to cut it from left to right, the sizes would vary. So we cut in and make these triangular slices if that were a cake, but you could get the volume of the cake by starting and doing these cylindrical shells. I also said it's kind of like a Swiss cake roll. When you unroll it, it makes a rectangular solid, which is what we call a cylindrical shell. So here's another visual where you're picturing these things whipping around and all the way around the y-axis, but this is the cross-sectional view. And so when it goes all the way around the y-axis, we get the solid, and the sums of all these cylindrical shells will give you the volume of the solid. So hopefully that's a little better visual. Then we went in, sorry, I forgot to hit record. I actually already did this once, but so you're going to get a shortened version at home. We went in and we tried to, one more time, show you the formula for shells. And again, I told them if you're dependent on the key for the homework one that says do shells, that's okay. For the washers, the discs, and the cross sections, which I actually did put on worksheet number 1, those you shouldn't be very key dependent. But I'm just going to draw that exact same. Maybe this was an upside down parabola and intersecting the x-axis, and we were going to revolve it around the y-axis, and it's going to make like a bundt cake. You have to picture that yellow stuff pulling into the screen, wrapping around in a circular fashion. And if we did it with washers, we would need to solve it for x in terms of y because we have to know how far we are. This is a dy problem, and that would get messy. And sometimes it's not even possible to solve for x in terms of y. So what we do is we take and try the shell method. And so we picture cutting in, and then this rectangular piece, like I said, is going to wrap around the y-axis and make a cylindrical shell, where if I cut it open, it would look like if you cut a Swiss cake roll open and you were staring at the rectangular thing that got rolled up. So this piece that I just made is kind of like the two-dimensional version of this cylindrical shell up here. And when I cut it open and lay it down, this is what it looks like. It's got a dx for its depth. The circumference of the circle would be its length, which is 2 pi r, and its height will be h. So when we integrate, we're going to be adding all of those up. So we're going to be adding up the volumes of all of those cylindrical shells. They are all length times width times height. So they are all length times, there's the length, times the width, times the height. And you might wonder, well, how do we get that r and that h? That's actually what's really nice, is that for the cylindrical shells method, we get to retain the dx, which is nice, so we can integrate from a to b, which is along the x-axis. the radius is just from here to here. And if I were to write what this point is, this is the point x f of x, whatever this function is. Maybe it was negative x squared, I don't know, minus 4x minus 1. I don't know what it is, I'm just making one up. But that's what that f of x would be, the height of the cylindrical shell. So the radius is almost always x, and the height is almost always f of x. So it makes it pretty simple. It helps you avoid doing the solving. Some people actually like shells the best, but you may not. And the next thing I showed them was, we did number 7 together on the worksheet. So the kids right now are working on worksheet number 1, right kids? How's it going? Good. Oh, great, excellent. All right, we did number 7. It's an interesting problem. We're going to derive the volume for a cone. 1/3 pi r squared h is what they tell you in geometry and what I write on your related rates problems and what College Board gives you if you have to work with a dripping cone. But why is it 1/3 pi r squared h? And it comes from revolving a line about an axis. I'm choosing the x-axis because it's the easiest. I told the kids why it was the easiest, but I'm not going through that again. So we revolve it around, and it makes a cone. This dimension right here would have been the height of the cone. This dimension right here would have been the radius of the cone. The function that we revolved around the axis is this line. All right? So we always get our radius by going from the axis of rotation to the inner edge of the curve. And we picture taking one slice out like this, and we add them all up. Each one is pi r squared h. So when we do our volume, we say this is going to be pi times the integral from 0 out to the height of the cone. Again, these are constants. If I ask somebody what is the volume of a cone, you'd have to give me a number for the radius and a number for the height. So I will integrate from 0 out to the height of the cone. If the cone was 10 inches tall, I would integrate from 0 to 10. The next thing I need is, well, this will also be a dx problem, right? I need the radius squared. That's in the formula. It's pi r squared dx. I need to figure out what this radius is. Well, it's the y value on the green line. So I have to write an equation for that green line in terms of x. Equations for lines are given in slope-intercept form. The intercept is 0. The slope is up r over h. So they told me in class today, well, that would be up r over h times x plus 0 for any cone laid like that along the x-axis. So when we do pi times big R squared, that's what goes in there. So I'm going to keep the pi out front. The r squared and the h squared can come out front because they're part of the constant. I'll integrate from 0 to h of x squared dx. When I integrate, I'll get x cubed thirds, right? And I will be doing that from 0 up to h. Fundamental theorem of calculus, you put the top boundary in first, subtract off what you get when you put in the bottom boundary. Bottom boundary is 0, so I'm just going to deal with the top boundary. It'd be pi r squared h cubed over h squared times 3. Now when I clean up that antiderivative, I end up with pi r squared h over 3, also known as the volume of the cone, pi r squared h with a third multiplier in front of it. So that was it for notes today. They're currently working on the worksheet. If a question pops up more than once, I'll come up here and do it, and I'll be recording that as well. So you might see some other ones pop up as videos. If all's going well, no worries. The worksheet is linked. It has the answers on it, but I will also link a key. So if I have, did I link a key yet? Like the full worked out one? I'll do that right now. So as soon as I'm done with that.